Okay, so in this video we're going to start graphing rational functions. We did it on the calculator in the previous example. It was this exact same function, but so I wanted you to see how to do that on the calculator, but I also want to talk about some of the specifics. So some of the vocab you'll see from the previous video, and then we're going to go through some other stuff that we have to work with when we're dealing with rational functions. So the first question, which is going to be a big thing here, is going to be the domain. And so as I look at this function, over to the side here to the right, I'm going to go ahead and talk about why we look at what we do. It's a fraction, can't have 0 in the denominator. So for any value that gets me 0 in the denominator, this would be undefined. Okay? So my domain is going to be listed as, so we want to look at what's going on in the denominator when we're talking about the domain. So I'm going to take what's in the denominator, and I know it cannot equal 0. So for my domain, I want to take the denominator and set it equal to 0, but I'm going to put it not equal to 0. And I'm going to just pretend like it's equal to, just solve it like you typically would. Well, I see that it's a difference of 2 squares, so I'm going to factor it. Or I see that it's just a squared term, and I can add 1 to both sides. The second method that I have on the screencast here is the more efficient one based on the setup of the polynomial. And so x cannot equal 1 or x cannot equal -1. So this piece right here, or, okay, it's the same answer, I just did it 2 different ways. So in order to write the domain, we would write it as x where x cannot equal plus or minus 1. And this is the appropriate way to write the domain. Now, it needs to be in this notation. We've talked about this in a previous chapter. And this implies right here that every other number will work for x other than a positive or a -1. If these numbers get plugged in for x, I would have 0 in the denominator, which makes it undefined. So they don't work. Okay? Now I'm going to go ahead and real quick, I'm going to graph this guy. And we're going to talk about what happens at these specific points. So I'll get the graph in red. It's not going to be the best picture because of the size of the graph, but we got our one hoop there, and one little J kind of shape here, and we have this little cubic guy going here. And these rational functions have these goofy looking graphs, and we talked about an inverse relation in the previous section, but this is kind of what we have. I'm actually going to erase this because I moved over a little too much, so I'm going to go ahead and be a little bit more precise here. Okay, and so that's what the graph looks like on your calculator. You just have to use your calculator. You don't have to worry about doing this by hand. What happens at these points? So at this point right here, which is at x is equal to -1, and at this point right here, which is at x is equal to 1, we have these empty spaces or gaps. And so what we do here is we draw these dashed lines through those points because x cannot equal 1 or -1, so there's no graph that is going to exist at these specific values. So the graph is empty, okay? And what we call these are vertical asymptotes. And we use this because vertical line is undefined, and it's an x equal to equation. And so where there's a restriction on the domain, there is a vertical asymptote. Now this is going to change a little bit when we proceed through this first half of Chapter 8. But so I would say the vertical asymptotes, and we'll just identify the previous problem. We'll look at that. We know that our domain was where x could not equal plus or minus 1. So the vertical asymptotes would be at x is equal to plus or minus 1. So notice the domain is listed with a not equal, and the asymptote is the equation of the two lines that go through those points. And that's how we identify our vertical asymptotes.